So let's go over the concepts you need to know for the exam for this. And this group did a very nice job on their whiteboard on what it is you need to know about. Throw that off to the Okay, so the first thing that you will need to understand is Coulomb's law. And here they have Coulomb's law. F is a force. Okay, that's the force of attraction or repulsion between two charges, 2 point charges. Okay, you've got Q1 and Q2. And it's directly proportional to the charges. It's inversely proportional to the distance between them squared. Just like the law of gravity is 1 over r squared, so is the electric force between 2 point charges. And by point charges, I mean 2 charges that are kind of concentrated at little points. And I really like this. They put the r hat vector, and that's not in your book, right? That's something we talked about. If it's positive r hat, if it's positive, that means they repel, because you have the same charge. What if you had 2 negative charges? What's a negative times a negative? Positive. Now what if you have a positive and a negative charge? That negative sign goes with this. It means it's an attractive force. They're pulling themselves together. That's what negative r hat means. Okay, here's K. This is the electric constant. And the electric constant is a property of our universe. It tells us how strong the electric force is given 2 charges and their distance apart. And it turns out that the electric force is insanely strong. Yeah, okay, and it's 8.99, or you can just use 9 on the test. 9 times 10 to the 9 newtons of force. That's, what is that? 10 to the 9. That's a billion, right? So that's 9 billion newtons. If you hold a Coulomb of charge here and a Coulomb of charge here, they're 1 meter apart. 9 billion newtons. Now, I don't know if you remember with gravity was 67 trillionths of a newton. You know, if you had 2 kilograms, 1 meter apart. So the electric force is incredibly strong. Okay, so I will give you, oh, and here's, it takes, I don't know, C, 6.25 times 10 to the 18 electrons or protons in a Coulomb. Is that what you mean by that? Yeah. Through this one? Yeah, so this is how many electrons or how many protons. I wouldn't put the divide. It looks like you're dividing it. But it takes 6.25 times 10 to the 18 electrons to make 1 negative Coulomb, right? It's negative 1 coulombs because the electrons are negative. Or the same number of protons to make a Coulomb of charge. So a Coulomb is just a big basket of charge. And it was defined before we knew what was carrying the charge. But now we know what the charges are carried by, electrons and protons. Turns out to make 1 Coulomb of charge, you need, what is 10 to the 18? That's a million trillion, right? Because a trillion is 10 to the 12, and a million is 10 to the 6. Well, this is 10 to the 18. So you need a little over 6 million trillion protons isolated to make 1 Coulomb charge. So that's a lot of charge. That's a lot of protons. All right. So here we have the definition of the electric field. I will give you a problem where I give you the electric field and a charge, and you'll have to figure out what the force is. Or I'll give you a force and the charge that's located at that point in space, and you'll have to figure out what the electric field is. And yes, it's measured in newtons of force per Coulomb of charge. Newtons per Coulomb. So yes, there will be an electric field problem using this equation. Make sure you understand what it means. Now, here is the electric field for a point charge. And look at the Coulomb's force here. F equals K Q1 Q2 over R squared. Well, you just divide it by one of the charges, right? The force divided by one of the charges, and you'll get the electric field at a point in space around a point charge. So make sure you understand that this definition right here, this one applies for all, no matter what, for all charge distributions. No matter how you distribute the charge, this will give you the electric field. This gives you the electric field, but only for a point charge or a charge that has spherical symmetry. Like if you took a sphere, a metal sphere, and put charge on it, it would give an electric field that would look like this. Okay. Now the electric potential. Electric potential is delta V, is the electric field times the distance you go through that electric field. And if you think about it, that looks a lot like work, right? Remember, work was force times distance? Well, voltage is electric field times distance, or displacement. And notice that this is newtons per coulomb times meters. Well, what's a newton times a meter? What unit is a newton times a meter? Well, it's a unit for work or energy. It's a joule, yes. It's a joule. So this gives you joules per coulomb, and that's voltage. And so a joule per coulomb is a volt. You will need to know that. You will need to know the units involved here. Okay. Let's see here. See, protons and electrons. Here's the charge on a proton. Here's the charge on an electron. And you can kind of get that from here. This number that you put on your whiteboard here is just a reciprocal of this.
We didn't know that.
Huh?
We didn't know that.
This one? Yes. This is a very good whiteboard right here, by the way. It's a good cheat sheet. Now, let's go back to this. So here's your definition for voltage. This is, potential energy, electric potential energy. I think that's what that E stands for. Delta U is change in potential energy, but what kind of potential? Electric potential energy divided by the charge. Gives you what we call electric potential. Okay. So here you can just multiply to find out how much energy is stored or how much work is done to push a charge through an electric field. Is the charge times the electric field, that gives you the force, times the distance, that'll give you the work done, or the energy stored. Okay. And then that brings us to the concept of capacitance. A capacitor is a device where you've got two plates hooked up to a battery of some kind, and the plates will push charge onto positive charge onto one plate, negative charge on the other. That creates an electric field between the plates, and there's energy stored in there. Now, how much charge you get divided by the voltage it took to get that much charge to be on that plate is a function of that device. It depends on how far apart the plates are, what the area of the plates are, what kind of stuff is between those plates, and so on. And that's called, that property of the electrical device is called capacitance. And it kind of makes sense calling it capacitance. It's how much charge you're going to store up on the positive plate per volt that you put across it. And think of voltage almost like, it's kind of like pressure. You're pushing charges through there. It's got energy, and those electrons want to get away from each other. So you're pushing the charge onto the positive plate per volt. And a Coulomb per volt, right? You got a Coulomb per volt. That's a farad. Okay, and so then here you've got, now you can just take this basic equation and solve it for whatever you want. Now usually capacitors have store very, very small amounts of charge per volt. So saying like 20 coulombs per volt. You don't see that very often. You'll quite often see millionths of a coulomb per volt. Or that micro right there, 10 to the negative 6. Picofarads, that's a trillionth. Nanofarad is a billionth. So actually you could put these in a different order. Micro, nano, pico. Farad. So those are just the metric prefixes. Micro, this mu symbol is a millionth, 10 to the negative 6. Little n is nano, that's a billionth. Like you've heard of nanotechnology, right? It's like very, very tiny. A billionth of a meter wide or something is a device. It's called nanotechnology. Pico, trillionths of a farad. And one of the things that you have in a capacitor is you have energy stored. And this really isn't in your book, it's just in your notes. And I think it's on one take-up test problem, but I do want you to know how to calculate the energy stored in a capacitor, since that's what capacitors do. They store energy. Okay. Now, one of the things that this group did that I liked and why I picked their board, and they've got a lot of the same stuff, is, well, they've got Coulomb's law, the electric field for a point charge, definition of voltage, stored charge on a capacitor, stored energy on a capacitor, here's the electric constant. So they got a lot of this stuff too. But they also included the rules for drawing electric field lines. And so electric field, you start at positive, end at negative. Never cross field lines. The number of field lines is proportional to the charge. And should represent the space around the charges reasonably well. I'll give you a very simple problem on the test to draw, electric field lines around. And then this other board, well, do you guys have that? You want me to take a picture of it? And then here's the other board, which really was chosen because it asked the ultimate question: will it blend? And I don't know. I know that remains an area of active research in physics today. Will it blend? Okay, that is all.